In this video, we're going to talk about what a differential is. And at the beginning, we're going to look at it from a graphical point of view. So I drew a random graph here of a function f of x, and I picked a point, and then I drew a tangent line to that graph. This is the tangent line at the point. And now what's going to happen is I'm going to say, okay, well, what if I move a little bit from here? So let's say I move a little bit over here to the right, and I'll call this change here delta x. Well, on your graph, when you move delta x to the right, your y value is also going to change, and it's going to change a value delta y. So delta y here, this is the change in the y value of the actual function f of x, or in other words, this is f at the right point minus f at the first point. On the other hand, if I move the same distance in the x direction, but now I look at how much did the y change on the tangent line, that's going to be dy. So dy is going to be the change in the y value of the tangent line. And the thing is, since it's a line, we can find the change in the y value very easily by just taking the slope and multiplying it by how far the x changed. However, how far the x changed is delta x, and what's the slope of the tangent line? It's just the derivative. So that means my differential dy is just f prime of x delta x. And if you think about it, if we call delta x how much the x changes on the regular graph, then we really should call dx to be how much it changes on the tangent line, but dx and delta x are the same thing because we're going the same amount to the right. We're just interested in how much the y changes. And so if you write that down here, it means that the differential that we're looking for is f prime of x dx. That is our formula for differential. Of course, if you're really thinking about it, you might be like, wait a second, we already know that the derivative is the same as dy dx, and if you multiply both sides by dx, you get that exact same formula, so why did I do all this picture thing here? Well, I did all the picture thing to try to understand graphically what we're talking about, but yes, it's the exact same formula. The only thing is, and I want to kind of give you a little warning here, is dy dx, that is a symbol for the derivative. It is not an actual fraction, which means you cannot just cancel things out like that. I mean, I do it and I happen to get the right answer, but it's something that you can't just, feel like free when you cancel it out whenever you feel like. It's not going to work. So just be careful with that there. But this is our differential. Now, for this problem here, the first problem, it says find the differential for a given function. Well, the first thing you're going to do is you're going to go ahead and find the derivative, and we can use the product rule here. Derivative first times the second plus the first times the derivative of the second. So we're going to have e to the x plus x e to the x. And then if they ask you for just a general differential, you would just take that and put a dx next to it. That's your general differential. But in this case, they asked us specifically x equal to 0. So I just plug that in down there, and you're actually going to get 1. And so this would be the differential at x equal to 0. Okay. And then the next thing is saying find the linear approximate or the linear approximation to a given function at a point. The thing is, they use this terminology in your book, but linear approximation, that just means tangent line. So I've had a lot of students in the past where I used linear approximation on the test, and they had no idea what they were supposed to do on it, and it's just because the book likes to change up what terminology they use for things. But linear approximation is the same as tangent line. So just think of that here. And we know how to find tangent line. We first take the derivative, f prime of x. The derivative of the square root is 1 over 2 square root of x. Then we plug in the x value to find the slope. So it looks like my slope is 1/4. Then I need the actual y value of the point, so I plug it in the original function. I get 2, and then I'm going to put this all together here. Y minus 2 is 1/4 x minus 4, and I'm going to get 1/4 x plus 1. So that is the tangent line. That is also the linear approximation. Now, once you have the linear approximation, we now want to approximate the value square root of 4.02. And notice the important thing here, it says without a calculator. It would be absolutely trivial for you to go ahead and plug this into a calculator and get an answer. So we're trying to do this without that. Now, because we're not using a calculator, our answer is not going to be perfect. It's not going to be completely right, but we're okay with that. And on the picture up here, the idea is the actual square root of 4.02, that would be the point on the blue graph, the actual value. But instead, we're going to find the point on the tangent line, the green graph. And even though they're not perfectly the same, they should generally be pretty close as long as our delta x is small enough. So what we're going to do is we're just going to take this linear approximation and plug in the x value of 4.02. So that'll be, sorry, not equals here, approximately equals 1/4 of 4.02 plus 1. Now 1/4 of 4 is 1, and 0.02 is going to be 0.005. So my approximation value is 2.005. And if you put it in your calculator, just to compare things here and see how accurate we were, in the calculator, the square root of 4.02 is 2.0049936766. So you can see it's definitely off, but it's off by a very, very small amount. And this was actually a technique that was used before we had calculators to find random weird values of our functions, like square roots, cube roots, sine, cosine. Like, what if I asked you what is the cosine of 0.07? You might have a really hard time doing that by hand, but now we can use this method to get our answer anyways.